this computer, right? So we have been talking about neutron stars and then black holes. So I guess I'm not going to summarize what we did last time because it's just yesterday that we finished it. Right, so we stopped right here yesterday. So we talked about how black holes are formed, and then different properties of the black holes, and then at the same time we talked a little bit about general theory of relativity and special theory of relativity as well, because they are directly related what we have been talking about black holes. And then I talked different phenomena that could happen close to a black hole, things like time dilation, gravitational redshift, and tidal interactions, those kind of stuff, right? And so where we stopped last time was everything that we have been talking is about different theories about black holes. The question is, do they actually exist? So do the black holes actually exist? So this is one of the long lasting problems that astronomers had, because even the theory predicted, nobody have ever detected the direct evidence of the black hole. But there are ways that you can get an idea that there are black holes. One thing is black holes cannot be seen directly. So let me take. So the black holes cannot be seen directly since the light is unable to escape from them, right? So we know about that now. So light doesn't escape from the black hole so that you can't see it. But the thing is, the materials that is being pulled down to the black holes may be tidally heated. So what will happen is, if you have, let's say, a star close to a black hole, these materials from that normal star will be accreted towards the black hole, and once they are accreted, they will get heated up, and once this material is heated, they give off X-ray radiation. So which means if you measure some X-rays using an X-ray telescope or something like that, then you should be able to conclude that there may be a black hole, right? So that's one way of detecting black holes indirectly. And the other thing is, black holes also exert large gravitational pulls on any close stellar neighbors. So which means the motion of nearby stars may provide indirect evidence of the presence of black hole. Now this is directly related what you probably have learned in general physics classes, even in the A levels. Now if you have an object at the center, and then if there is another object that's moving around it, if you know the properties of that object that is moving around from the circular motion, you probably can get an idea about what is at the center, right? Doing some calculation. A similar way, the motion of nearby stars may provide indirect evidence of the presence of a black hole, right? So that's another way of detecting black holes. And sometimes there are some binary star systems that have one visible star plus a companion seen only in X-rays. So there are binary star systems, which we will also talk in the next lecture. When you have this binary, if you have a binary system that you can see one of these visible stars, and you just see X-rays coming from another companion star, that which means you can't see that particular star, but you will see the X-rays coming from that. Then also you can conclude that there may be a binary star, right? So the example is Cygnus X1, probably you have seen it before, right? Now, this is an example like accreting matter from, so this is just an artistic picture that there is a black hole right here, and then there is matter that is accreted by this star right here. So once the matter is accreted and get heated up, they will emit these jets of X-rays towards this direction right here. So which means if you can detect these X-rays, you can conclude that there may be a black hole at this particular position, right? So that's one of the ways that you can detect black holes. Right. And here is an example that probably you can detect a black hole like that. And just go through this link right here that I have put on. You can just go and directly read about that. So I'm not going to explain it. And here is another example. One of the things that I mentioned there. Remember that one way is using tidally heated gas emitting X-rays, and another way of detecting black holes is looking at the motions of the nearby stars, right? Now this is what we are doing right here. Now here is an example that how we conclude that there is a supermassive black hole at the center of our galaxy. These are some stars very close to the center of our galaxy, and if you measure the motion of these stars, as I told you before, I can conclude that there is a very massive object right here. And this massive object is, now we assume that a supermassive black hole, and this particular object has a name now, which we called as Sagittarius A, right? So that's a name given for the star. Now all these objects are moving on Keplerian orbits, which means you can use the Kepler's law and then find more details about these objects and then conclude what is the mass right at the center. Right. So you also have a link right here so that you can go and directly see some more details about. These are actually actual calculations that astronomers have done to detect what kind of object that is, which is at the center of a black hole. Right. So these are like indirect observations for the black holes. And there is a direct observation that we can talk about black holes, which is gravitational waves. And sometimes you may have heard about gravitational waves. This is one of the very popular topics uh, that was that have been talking by astronomers now for a few years. And detection of gravitational waves actually has happened not a long time ago. It is just like a few years ago, around 2016 or 2017. So what has happened actually, according to the general relativity, any arrangement of matters, just give me a minute, there is a disturbance right here in my mouse which doesn't move up. Just give me a minute, wait for a minute.
මේ Zoom එකේ lecture ඉන්නකොට රත් වෙනවාමයි. අපෝ මගේ නම් ගෙදරදිත් එහෙම වෙනවා.
Right. Now let's see the rest of the lecture. So it's fixed now. Right. According to the general theory of relativity, any arrangement of matter, let's say from a sphere to a sausage shape, create a disturbance in space-time. Now, this disturbance is called a gravitational wave, and relativity predicts that it should spread outward at the speed of light. Now, what I am talking here is one of the direct evidences for gravitational waves. And so this slide basically explains how the gravitational waves can occur. And one of these examples is that when you have a very huge mass, and if there is a rearrangement of matter in this mass, then what happens is right. So let me. Right, so sorry about that. There were some disturbances here, so I just make it right. So what I have been talking about is the detection of black holes, the direct detection of black holes. And so these direct detections came from gravitational waves. And what that means is, if you have a very huge mass, and if this matter is rearranged on the space, this rearrangement will make disturbances in the space-time, right? And then we also call this as ripples in the space-time, and they have a name which we call as gravitational wave. Now, remember that these gravitational waves do not appear in our normal electromagnetic spectrum. This is completely different and out of our electromagnetic spectrum, right? In normal, under normal circumstances, we know every wavelength range in our electromagnetic spectrum, starting from radio waves, radio waves, X-rays, and those kind of stuff. So that this is what we have been talking up to now, how we detect things using X-rays and radio waves and visible light, X-rays, ultraviolet, those kind of stuff. But gravitational wave is completely different. These are occurred due to the rearrangement of matter, and this is also called as ripples in space-time. That there was nothing that we could detect these, and also these signals are very weak. And at the same time, these gravitational waves are predicted by Einstein's theory of relativity. And what happens is, these since these waves are tremendously weaker than electromagnetic waves, they are very difficult to detect. And theoretical calculations suggest that some of the most likely events that would give a burst for these gravitational waves are strong, that are strong enough to measure, are these right here. So let me get the merge of two neutron stars in a binary system that spirals together until they merge. Now you know what is a neutron star. Now, by merge, in the process of merging two neutron stars in the space can give rise to gravitational waves that we can detect from Earth. And the reason actually that we talk about specifically about neutron stars and black holes here, those are the objects that could give gravitational waves that we can detect from our Earth, right? So that's the idea. And shallowing of neutron star by a black hole. So that means again a combination of neutron star and black hole. And then merger of two black holes, those kind of things. So when two black holes merge, and you can think about their masses, they are probably the huge or the probably the most dense objects that you can find in the universe. And when these two may merge together, their gravitational waves are very, very strong. And even though they have traveled a very long distance up to the Earth, if we try to detect those, there is a way that we can detect those gravitational waves, right? So that's the idea. Now, in the last 4 decades, the scientists have been developing an experiment to try to detect gravitational waves. Now, we know how to detect all these electromagnetic spectrum, but we didn't know how to detect these gravitational waves. Now, scientists have been trying to develop an equipment that they can detect these gravitational waves for the last 4 decades, and they were actually successful at the end. And now we have a detector to detect gravitational waves, and the name of the detector is Laser Interferometer Gravitational Wave Observatory, and in short form we call this as LIGO, and some used to pronounce it as LIGO as well. So what this does is, here is a picture of the gravitational wave telescope. I mean, this is not actually a telescope like a real one, but we used to tell that it has a gravitational wave telescope. And this is actually Livingston, Louisiana in USA. This is where it is located. And you can see that there are very long two arms right here. There is an arm from here to here, and there is another arm from here to this direction. So these are two long arms. And as the name suggests, actually they use the theory of interference to detect these gravitational waves. Now, how they do is that they have some kind of mirror right here, and they send the signal through this arm, and this is around 4 kilometers long, and this is the same distance, 4 kilometers long. And these equipments are very precise, that they would detect even a smaller disturbances that would happen on the space. And the way that they detect this is using the theory of interference. Now, I don't know whether you have done this experiment in your practical labs. There is something called interferometer, a small equipment that we use to shine a laser to two directions, and then you combine these reflected waves to measure the interference pattern. And there are two types of interference. You probably know that in constructive interference and destructive interference. And if you have some kind of path difference between two waves, then you would see this difference in the interference pattern, right? So that is the idea. Now here also they have made this equipment in such a way that if they show a disturbance in space-time, this particular equipment will detect it as a difference or some kind of change in the interference pattern that would come through uh, the equipment. So that's the basic idea behind that. Right. So what has happened with this experiment is, once they made this equipment and started working, I guess around 2016, as far as, yes, it's here. It's 2016, 11th February, for the first time in the history of LIGO, team announced that they have detected gravitational waves from the merging two black holes. So once you detect a gravitational wave like this, then you can do the calculations depending on the wave that you have detected, to see what kind of wave, what kind of objects uh, probably be responsible for this gravitational wave. So that's how they did it. So they found that gravitational waves produced by merging two black holes, and they found the masses of these black holes as well. One black hole is 20 solar mass and the other one was 36 solar masses. And this has happened 1.3 billion years ago, and you can see the distance, how far away that was. And during this merger, the 3 times the mass of the sun was converted to energy, and I have put inside the brackets, recall E equal mc squared. So that's how you convert mass into energy, and you can think of the amount of energy that have created during this process. And even produce power about 10 times the power produced by all the stars in the entire visible universe, right? So you can see the amount that I don't want to explain about that. But the power was all in the form of gravitational waves, and hence was invisible to our instrument. The problem is here the power is completely come in terms of gravitational waves that we cannot detect from any equipment that exists with us, except this gravitational wave LIGO experiment. But even when they come into the earth, the signal is so weak that you have to be very precise with your equipment to detect that. Now here are the actual waves that they have detected, and on the right hand side what you see here is just a picture that they think what has happened. Remember that this is not a real picture. Once again, this is just a picture that just made by someone. But this image right here, you can see that the first wave right here is detected by LIGO Hanford, which means one gravitational detector, and there was another gravitational detector in Livingston, which is a different city, and they have detected this one right here. And remember, because of the difference of the distances they have for these detectors, so once you detect it from one place, then you can assume that the other detector should detect the same thing after a certain time, right? So this is what exactly have happened, so that they can confirm that their detection is real, right? Because when you detect a thing, something like this, which has a very weak uh, which is a very weak signal, you need to be careful, because it is possible that you sometimes can detect some of the other signals that are actually not gravitational waves, right? Now, for example, I have a lot of stories about that, which I do not have time to tell all of them. But what would happen is, at the beginning, when they were started this experiment, sometimes they were excited about seeing some of the signals that are coming. But eventually, sometimes there is a bird that is just was sitting on one of these arms and those kind of stuff. So they have created this small interference pattern. So they have done tested this again and again, and they have isolated, because even there is a larger vehicle going on nearby highway that could create a small wave as well, which can be detected by this interferometer. So they eventually actually they remove all these signals and make sure that they are only detecting these gravitational waves, right? So that's how they came into this position. Now, detection of the gravitational wave, you can see that in this third picture right here, they have the two waves shifted each other, and then there is, okay, so in both these pictures, I don't know whether you can see, there is a theoretical curve that also goes with this, which is exactly matches with the experimental data. So that's how you decide that you have exactly figured out or detected the gravitational waves, and how theory and experiment agree with each other. I mean, look at the presentation that you have, you will see that there is a small line that goes on as well, which is the predicted line from a light color, and it exactly match with what you have from the experiment. And also this last picture right here, this one is just by shifting the wave patterns of two detectors, just do a little time shift to check whether they are the same. So they exactly matched with each other, just to confirm that they have detected the same wave, and they are the gravitational waves that came from merging of those two black holes, right? So this is why this made the big news among media as well. The first time ever in the history that we have detected the gravitational wave. And the people actually who leaded this project is one of the famous scientists called Kip Thorne. Probably have heard about him. And they were awarded the Nobel Prize in 2017. Right, so this is an schematic diagram, if you need, how it looks like. Here is the laser interferometer, that one wave comes from this direction and the other one comes from here, and they were combined each other. and going to this detector right here. So basically a laser is emitted from here, and it will go up to here, and there is a splitter, a beam splitter that will split the laser light to this direction and that direction, and they will go through this path and then come back, and this path and come back. So what will happen is, if a gravitational wave is detected, they will slightly shift the space time right here, so that the path difference, detected path difference, will be different, right? So that's what would happen in this experiment, right? Now this is the direct detection of the gravitational waves, and then here comes the next phase of the detection of the gravitational waves again. Now this is actually capturing the event horizon of a black hole. And now you know what is an event horizon, right, for a black hole, which is the area that you see using the, you can calculate using the Schwarzschild equation. Now, on April 10, 2019, this is not a long ago, this is actually last year, EHT collaboration, EHT means Event Horizon Telescope collaboration, presented their first results, an image of the supermassive black hole in galaxy M87. So this is actually considered as the first ever image of a black hole. Actually not the center of the black hole, but the surrounding part, which we called as the event horizon. So what they have done here is, you are probably wondering that since we cannot detect the black hole, how on Earth somebody has made this picture. Now this event horizon telescope is actually not a one single telescope. So there is a network of telescopes that they are operating together, and they are looking at one particular position, that where they think that there is a black hole, and then they capture all these radio waves, as far as I remember, yes, and then coming from these uh, that particular object from these different telescopes, and then they merge all this data together to make this image, right? So that's how they create this, right? And this is actually later what they have detected from the same event horizon telescope. I guess this is 1 or 2 months ago, not so long ago. So they have detected something called distance quasar. They observed with the finest details, and the these are actually the jet produced by a supermassive black hole. So that's why they are important. So what we believe is, quasar is also called as quasi-stellar radio sources, and quasars are believed to produce their energy from massive black holes. So that is also an evidence that there is a black hole, right? Right. So these are some information, I guess, should be in one of the previous slides about distances and masses of these combining black holes to produce images. And I don't know whether you can, this is actually what has happened, right? Before I start this, let me show you. I don't know whether you can hear this or not. This is actually a video that shows you the sound of colliding black holes. And I got a question from one of the students I guess last week, asking that how these things are create sound, because the space is vacuum and we should not hear sound. And that is completely true. uh, these objects actually, the coalescence of the black holes do not create sound. What has happened is, once they detected these signals, the scientists have converted it to sound wave so that you can hear it, right? So that's what has happened. Now I am going to play this, since it is not a long video, but I don't know whether you can hear it or not. But if you have the the PowerPoint with you, just play with it, and you will see that a sudden two like different sounds during the video. So those are the points where we think that the two black holes have merged and created that sound. Let me play this. I don't know whether you can hear it or not, as it comes from the This little chirp sound that you probably hear, I don't know whether you can hear or not, that is the sound that we believe that came from this, the merging of two black holes. So just watch the video. I'm not going to play with it too much. Right. So that's the end of that section about the black holes. Right. So there are two other slides. So let me finish that as well. Just to summarize everything that we did about the stars. Now, that conclude the final stage of the stars during this stellar evolution. So what I have been doing right up to now is just talking about the stellar evolution with different phases. Now, if I summarize everything, this is actually what happens. To become a white dwarf, a star should have a main sequence mass less than 8 times the solar mass, and the final mass of a star should be less than 1.4 solar mass. That is also considered as the Chandrasekhar limit, if you remember. For the neutron star, when the star is the main sequence, it should have a mass between 8 solar mass and 25 solar masses, and the final mass of the star should be 1.4 and 3, between 1.4 and 3 solar masses. So that's the limit for neutron stars. And then for the black holes, the initial main sequence mass for a star should be greater than 25 solar mass. So anything greater than 25 solar masses can create a black hole. And the final mass at the end is maybe greater than 3 solar masses. So those are the limits for stars to have to be in these different phases during their lifetime. So basically you can see that it's the mass of the star that determines what will happen to that at the end. Right. There are some actually some kind of different myths about the black hole. So people used to say that black holes go about sucking things up with their gravity. So people think that they move here and they are sucking everything that get close to the black hole. But the truth is only very close to a black hole that the strange effects we have been discussing come into play. So you didn't need to worry about a black hole that are like billions of light years away, because that will not affect to us. So that's the true situation, right? This is just for your information. Right. So while I am finishing that section about the black holes, let me come into the next one, which is about stellar motion. Right. So this is about stellar motion and binary stars. Remember what I have been talking up to now is different phases of the stellar evolution, but I did not talk about how stars move and on the sky, right? So this particular section is about the different movements of the stars on the celestial sphere, and also binary star systems, which is actually a different field of research, right? Now, when you look at the sky, what you see is stars appears to be fixed in their relative positions, which means when you look at the sky, you always see that they are in kind of in a fixed position. Of course, all the stars rise from east and they will set from the west at night. But if you look at a group of stars, those seems to be appear at the same fixed position, right? Relative positions. Now, so what actually has happened is this illusion is caused by very large distances to stars, because we are looking at very large distances now. Then it seems to be like that. But in reality, the stars move with respect to each other. and change their relative positions. Actually, stars moving with respect to each other and change their positions. Now, if stars are moving, they should have a velocity, right? So there are actually a few different kinds of velocities that related to stars. One type is called radial velocity. Now, if you, I guess all of you know about the Doppler effect, and if you look at the Doppler shift of spectral lines, when spectral lines moving star shift towards the red end. So if the spectral lines are moving towards the red end, which is towards this side, then what that means is the stars are moving away from us, right? So that all of you know about that. Now, if a star is moving towards us, then you would see the lines will be blue shifted, right? And you can just look at one of these lines and compare this one right here is more red shifted, this set of lines compared to this whole set of absorption lines, right? So that's how it works. So that's one way of measuring the velocity, but this particular measurement will tell you about the radial velocity, and usually measured in kilometers per second. So what that means is along the radial direction, you can tell that whether the star is moving away from us or moving towards us, and also in what speed. There is another type of motion which we called as proper motion. So the proper motion is the change in the relative positions of the stars on the celestial sphere. So when you look at the sky on the celestial sphere, you would see that the stars move across the celestial sphere, not away or towards us. That type of motion is called as the proper motion of a star. And here is an example of a proper motion. These three images are taken at different years, 85, 95, and 2005, 10 years apart from each other. And you probably should be able to identify that there is a star that moves across the sky and in a different position, right? This is star right here, which I am marking. So that is called Barnard star, which is actually the star that we know that is known to us as one of the stars, probably the star that has the largest proper motion on the sky. And it is called Barnard star, which is one of the popular star because of its larger proper motion that moves fast across the sky during the time that it has measured. So this, and still you can see that even the Barnard star, it's relatively slow. You can see the change in the position over 10 years of time, right? So during one night, if you are observing, you will not be able to even detect this. Now these changes are very slow. Even the star with the largest proper motion takes 200 years to change its position in the sky by an amount equal to the width of the full moon. Now, you know, when you look at the sky on a full moon day, you can roughly get the idea about the width of the full moon. To, to move a star which has a larger proper motion amount of distance by equal to width of that full moon also take around 200 years, right? So you can see that how slow is it, and this is why you can't detect these proper motions. And here is an example what will happen to the Big Dipper constellation because of the proper motion. Now this picture right here, this picture right here is how the Big Dipper constellation looks like 50,000 years ago. And this one right here is how it looks like today. Now this is what we see, right? So this is this is what we see today, and this is 50,000 years ago. But after another 50,000 years from now, you can see that from arrows I have marked here the directions of the proper motion of this star. Because of this proper motion, after 50,000 years, the shape of the constellation will be changed like this, right? So that is what you have to learn. This is as a consequence of the proper motion. Since the time span is very large, we will not detect it during our lifetime, but that will happen. Right. So this picture right here basically explains all these kind of motions together. This arrow right here represents the radial velocity. That means the velocity, uh, the, the velocity away from us, which means towards the radial direction. And this one is called actually the transverse velocity. So what, instead of transverse velocity and the proper motion is actually connected to each other. Instead of measuring the transverse velocity, what we are measuring is the proper motion. Proper motion has a unit of like arc seconds per year, those kind of unit like that. So what we do is we measure the change in the angle and the distance to the star. That will give us the proper motion. And if you need, you can convert it to transverse velocity. So these two are like connected to each other. But to convert this change in the direction to a speed, say kilometers per second, it is also necessary to know the distance. Now you can measure the angle and change, see what angle it has changed. But if you need to convert it to this velocity, then you need to have the distance, right? So that's the idea, right? Now the space velocity is, let me go back to the previous slide. The space velocity right here is the resultant of transverse velocity, which comes from the proper motion, and also the radius velocity. And this is actually also the true velocity, combining of those two. Now, what happens is this movement of stars, if you think about the space velocity, to know the true space velocity of a star, that is the total speed and the direction in which star is moving through, we must know its radial velocity and the proper motion and the distance. So you need to know three things to calculate this space velocity: the radial velocity, and then the proper motion and distance, which can be converted into the transverse velocity. So once you know those two, you can calculate the space velocity, right? So these are two vectors now. So you can combine and calculate those that at the end, right? Now, over several 100,000 years, these changes can be large enough to affect the apparent brightness of nearby stars. So what happens is this change in the space velocity can even affect the apparent brightness of stars that are nearby. As an example, if you think about this, the star Sirius, which is in constellation Canis Major, or the big, we also tell Big Dog, is the brightest star in the sky about 100,000 years ago. The star Canopus in the constellation Carina was the brightest one, which is actually 100,000 years ago. Right? Now Sirius is the brightest star now, but 100,000 years ago, because of this space velocity or the motion of the stars, there are different stars that appeared as brightest stars. Right, so the next thing is about the rotation of stars. So that's about the motion of stars. That means how stars move, and all stars also rotate. So that's another thing that we are looking at. Rotation of stars also can be detected using the Doppler effect. So if an object is rotating, then one of its sides is approaching us while the other is receding. So that's what will happen if a star rotates, and if you look at the Doppler shift of that, what you would see is the one side will be blue shifted and the other side will be red shifted. So that's what explains here. And if the star is rotating rapidly, there will be a greater spread of Doppler shift and all its spectral lines should be quite broad. And in fact, astronomers call this as line broadening. So it is important that you remember this term right here, line broadening. So what that means is, you will see in this picture right here, this star right here is a not rotating star, and it has a spectrum and there is an absorption line, which means that you have a dip like that. But when the star is rotating, this absorption line broadens because now this part is moving away from us, and this in this side it's coming towards us. And because of that, you will have a line broadening like this. So which means this line, the same line will be broadened because of the rotation of the star. And this amount of width of this line can give you an idea about the rotation speed as well, and this is called line broadening, right? So this is another two stars that rotates, right? So that's about the rotation of the stars. Next, I would like to talk a little bit about the binary star systems. So as you know, binary star system is there are two stars together and one is moving around the other star. So these type of star systems are called binary star systems. And there are different types of binary star systems depending on how we detect them. The first type is called visual binaries, which means they are sufficiently close to each other and can be seen two stars individually from the telescope. So which means these two stars, if you look from a good telescope, from a telescope, then you should be clearly see that there are two stars that are very close together and one is moving around us. So these type of stars we called as binary stars, we called as visual binaries because you can directly see those. But there are certain binary stars that you can't see it in that way. And another type is called astrometric binaries. So these are detection of an unseen companion of a binary star by gravitational influence on the primary star. Now what happens is, you can see there is an equation right here calculating the mass of the binary system. So if M1 and M2 are masses of two stars, if A is the total separation between the centers of two objects, and if the P is the orbital period, what you can do is, if P and R between stars can be obtained, then the sum of the masses of two stars can be calculated. So you can calculate the mass of this system if you can find the period and the separation between stars, right? Now this method is useful when the binary system is too far away and the stars are too close, or one star is so much brighter than the other, right? So these are like experimental methods that we use to detect binaries. So astrometry means you are making measurements to detect the binary star. So if one star is very bright, of course you can't then resolve the two stars, but from this method you can detect that there is a binary star system. And the third one is called spectroscopic binaries. So that means the star which appears as a single star when photographed or observed visually through a telescope, but which the spectroscopy shows really to be a double star, is called, double star means again the same as the binary star, is called a spectroscopic binary. So which means when you look at these kind of star systems visually, you can't resolve those two. You just see one, just like a one star. But if you look at the spectrum of the star, then you will easily conclude that there are two stars. So those type of stars called star systems are called as spectroscopic binary. So here is an example. So there are two stars and you can see two lines, but depending on how they move, once they are combined together in this particular arrangement, then you will see one line and then again one line right here, but two lines again. So from those kind of observations, you can detect that there are actually two stars, not one star. Right? Just read through, since I do not have time, I'm not going to explain each and everything here, but just make sure that you go through these wordings. So this is that is why I have put it here, in case if you need to read it through, you can get information from here, from this caption as well. Right. So this is radial velocities in spectrum binary. So these curves plot the radial velocities of two stars in the spectrum of a binary system, showing that how the stars alternately approach and recede from from Earth. You can see that one star is going away from us, then velocity is decreasing, which means it's going away from us, then coming towards us, those kind of things, right? So just read through it. You can easily understand the concepts here. And then the last one is called eclipsing binaries. This is also one of the popular ways of detecting binary stars. So let me directly go to the picture and show you what eclipsing binary means. Now you can see that there are two stars. The star now right here in this example, this star from this I would say this is purple, probably purple color, is a large star at the center, and there is a small blue star that is going around it. So what has happened is, as you see here, there are two dips at number 2 and number 4, which correspond to these numbers, number 2 and number 4. Now, if you remember that um, basically the brightness of a star basically depends on two things. The one is the temperature and the other thing is the surface area. Now, if you read this caption, you will see that here the blue star has a higher temperature compared to this large star at the center. So what has happened was, when this, of course, in the position 1 and 3, when you look from the Earth, what you would see from a telescope is you will see the light coming from both the stars, right? Nothing is covered by the other one. So the both stars can be seen at position 1, in both position 1 and 3, which means you will get the complete brightness from both stars, which means they are correspond to number 1 and 3, that you don't see any drop in the brightness, right? But then after that, if you look at the position number 4 and 2, one star is covered by the other one at both positions, and you can see at position 2 you have a larger dip, and position 4 you have a slightly smaller dip. Can anybody explain why you have a smaller dip here and why you have a larger dip, depending on the properties that you know about stars? Is there anyone who likes to give an answer? Right. So the reason that you have a larger dip right here at the number 2 position, you can see that at number 2 position, you have the purple colors large star at the front, and this small blue star is completely covered. But the thing is, even though it is smaller, the blue star, is the one that has higher temperature, right? If you remember the luminosity equation, it was uh, A is the surface area, and then T to the power 4, and there was a constant like sigma. A is basically 4 pi r square, right? Now T is T to the power 4, which is the temperature. Now you can see from this factor right here, the temperature plays a major role for the brightness of a star. Now this is why, even though this small star right here, small star, even the star is smaller, since it is very hot star, when it is covered, you will lose a considerable amount of brightness from the system. So that's why you have a larger dip or larger loss of brightness. But when it comes to the position 4, still you will lose some brightness, because you can't see the blue star covers a portion of this large star, but not the whole star, right? So if it is just a portion of the star from the large one, but that portion is small and you just lost it from the area of the largest star, right? But still there is a large area that you can still see, and this is why you have a smaller dip right here. Right? You don't lose that much light in that configuration. And make sure you understand these things logically so that you don't have to remember, right? And one last slide right here, the mass luminosity relation. So this is a relation that actually can be used to find the mass of a star if you know the luminosity. So it turns out that most of a star's mass and luminosity are related, and in fact this is roughly the relation. Sorry. So this is roughly the relation. L is roughly equal to 3 m to the power 3.9, and people used to consider that m to the power 4 as well. This relationship is known as mass luminosity relation. So that's what this graph actually explains, the mass luminosity relation. So these things I mean, if I were you, I would remember this relation, right? At least L is approximated by m to the power 4. So these plotted points actually, they are actually representing the mass and the luminosity of stars. Now there are 3 points that are lying outside this particular line that you see. These are actually white dwarfs, so they act like a little bit differently. So they are below the sequence of points. Right, so I just have 2 examples here. If 2 stars differ in mass by a factor of 2, so that means more massive star one will be 2 to the power 4 times, or about 16 times brighter. So the massive star will be brighter, right? If you have 2 stars, one is massive, 2 times massive than the other, the massive star will be 16 times brighter. So that's what, if you go back, this relation tells you, right? Assuming that roughly this value 3.9 is equal to 4. So you can assume that L is roughly approximated to m to the power 4 as well. So there is no problem of assuming that. So you have another example, same thing like this here, right? So that's the end of that lecture.